Hello friends, good morning. And I know it's been quite a long time since we've met, almost 2 months now. I hope you've productively utilized those 2 months. And I'm just giving it a try to record a few videos which I believe would probably help you better in learning the subject. Now I'll try to deliver the 6th module of Geotechnical Engineering 1 now, and which happens to be the last module of your subject CE208. Now I believe we have already covered the 4th module up to the 4th module during the class contact hours, and I believe you have all got the 5th module, the slides of which were converted into a PDF format, and I believe you have all got that. And the 6th module, these are the contents, by the way. The contents of the 6th module includes the stability of finite slopes and the compaction of soils. Now the detailed content is given in here, or you can refer your syllabus if you have a copy of that with you, but nonetheless I'll probably start with compaction of soils. Now why I start with compaction is that this is somehow a continuation of the engineering properties that we were discussing. If you remember back in the first module of the subject, we said a few introductory sentences, and the first module was kind of an introduction to the subject, soil mechanics or geotechnical engineering 1. And while discussing the first module, we had said that soil as a material can have two different properties. Number one is the index property, and number two is the engineering property, right? So the index property happens to be the ones that include the Atterberg limit, the relative density, the particle size distribution, etc., wherein you are using some indices to classify the soil. Right? So the index properties were included in the second module, and from third module onwards we were dealing with the engineering properties. And the third module, if I recollected correctly, it was about permeability, and later on we moved on to shear strength, which is the second engineering property in the subsequent module. And in the 5th module we started off with the property called as compressibility. Now in compressibility you have two divisions. Number one is consolidation and number two is compaction. Consolidation was discussed in the 5th module, and the 6th module here we'll try to discuss at least peripherally what compaction of soil is. Now, as the name suggests, this is nothing but a reduction in volume, right? If you have a volume of soil, you are trying to compact it down, by which you are reducing its volume. Now the predominant difference while we talk about compaction and consolidation is that in consolidation the reduction in volume is due to expulsion of water, whereas in compaction the reduction in volume is due to expulsion of air. Now you can see a picture here, which is a roller compactor, by the way. At least a few of you might have seen such an equipment in construction sites. This one is used to compact the soil. Why? Because we want soil to be of a higher strength, right? We don't want the soil to be loose. We want it to be compacted. Likewise, there's another thing called a dynamic compactor. You have a big hammer which is lifted to a height, let's say 12 meters above the ground level, and it's allowed to fall. So that's a dynamic compactor that you see to the right side, and to the left side you see a roller compactor. These two examples, the pictures, are examples of compaction at site. Now what really happens in compaction is shown in this figure, right? It's quite similar to the three-phase system diagram. You have solid, you have water, and you have air. So when compaction happens, the soil gets compacted to this form. You can compare these two pictures and say that the solid particles and the water particles, which are marked in blue color, by the way, has not reduced the volume, whereas the air, which is the white color void spaces that you can see, has got subsequently reduced, right? So this reduction in volume is entirely due to the reduction in air spaces or the expulsion of air. So fundamentally compaction is done to improve the engineering properties of the soil, and it's nothing but pressing of soil particles to each other by the mechanical process, and it involves expulsion of air. Quite simple theory. Now this obviously increases the density of the soil and decreases the void ratio. Now I'll try to explain this using the three-phase system diagram. We discussed the three-phase system diagram in the first module, right? And we were saying that this is one fundamental principle which can help define the properties of soil. So we'll move to the three-phase system diagram definition here. You can see two pictures there. To the left side, I'm trying to explain the compaction, and to the right side, I'm trying to explain the consolidation. Now in consolidation, if you have already gone through the notes that I had shared earlier, you can see that the soil is completely saturated, which means you don't have air spaces, you just have water and you have solid. When consolidation takes place, there is a reduction in volume, which is entirely due to the reduction in water volume, right? You don't have air, so every reduction in volume is due to the expulsion of water. So that is what happened in consolidation. Whereas to the left side here, you can see compaction. You can see there's solid soil, you can see there's water, you can see there's air. Now this reduction in volume is due to the reduction in air, right? You can see the difference here. Earlier case in consolidation, you didn't have air and the reduction in volume was due to water expulsion, and in compaction you have a reduction in volume which is entirely due to the expulsion of air. So that's a primary and the predominantly difference. Nonetheless, there are a few other differences which I've listed in the table here. To the left side you can see compaction, and to the right side you can see consolidation. So essentially compaction is a sudden process of volume reduction, whereas consolidation is a gradual process. Compaction is usually dynamic loading, whereas consolidation is a static loading, right? We were talking about the example of a sponge in consolidation. Compaction, it happens in partially saturated soil, whereas consolidation happens in a fully saturated soil. Compaction is by removal of air, whereas consolidation is by removal of water. Compaction is an artificial process mostly, and consolidation is mostly a natural process. Of course, there are differences there, but nonetheless, for theory's sake, you can say that compaction is artificial and consolidation is natural. Now, if you remember the day I had taken you to the lab, there was something called the Proctor compaction test. I'm not quite sure if you remember the setup there, but you had a Proctor compaction setup there which quite resembled like this. You had a mold, you had a hammer, and you were fundamentally trying to push in or squeeze in the soil into the mold. So Proctor compaction test is one test that's usually conducted in laboratories when it comes to engineers to test the density of soil, right? Let's take an example. When, let's say you are an engineer at site of a highway construction and you would like to see the density of soil that you should employ at site. So what usually the site engineer does is he takes a chunk of sample of soil. He usually takes around 5 to 6 kilograms of soil, get that carried to the laboratory and try to see at what water content will the soil attain the maximum density. So that is a density that the engineer is interested in. You can add water to the soil. You can try to see at what water content will the soil attain its maximum density, right? So this test gives you the water content at which the soil attains the maximum density and the value of the maximum density, right? It's quite a simple test. No big rocket science is involved. Now, it's carried out to decide on what amount of water and what degree of compaction is required in field to attain a target density. For instance, if the site engineer specifies that the density that he prefers is 1.8 gram per cc at site, you'll be asked to carry the soil to the laboratory, test it, and give back a data which would tell you the water content which will give 1.8 gram per cc. Just an example, right? Now this test provides the relation between the water content and the dry density. Now the Proctor compaction test is usually two in number. In practice, number one is a standard Proctor test wherein you have a mold of around 12 centimeter height and 10 centimeter diameter. with a detachable base plate and a collar, the cross section of which is shown in this slide. And you have a hammer which is 2.6 kilogram of weight with a free drop of 31 centimeter, which means you raise the hammer, as you can see in this figure, you raise a hammer, you drop it, so that drop height is fixed to be 31 centimeters, and the weight of the hammer is 2.6 kilograms, right? And the soil is usually filled in 3 layers, with each layer given 25 blows. So what you fundamentally do is you keep one layer of soil here, you apply the dynamic compaction using a hammer, you give 25 blows, and you add the second layer, you do the same procedure, you add the third layer, you add the same procedure, and you finish. So that's a usual procedure, the details of which is given here. You take about 3 kilograms of soil, and the initial water content is determined using an oven dry method, and the water is added to make the initial water content about 4%. This is just an example. It depends on the type of soil and the conditions in field, but nonetheless, for the sake of an example, I can say it's around 4%. And the soil is thoroughly mixed then, and then you find the empty mold weight, right, which you can mark as M1. The mold weight is marked M1. Then the soil is filled in the mold in layers by blows using this hammer, which has got a weight of 2.6 kilogram and has a fall height of, like we said, 31 centimeters. You fill this mold using this hammer, right? The extra soil at the top here is trimmed off and the assembly is weighed. So earlier you had an M1, now you have M1 plus the weight of the soil. This is M2, right? So fundamentally, the mass of the soil inside the mold will be M2 minus M1, which I've marked as M, from which you can calculate the bulk density of the soil. So this is quite simple. You get the weight of the soil inside this, which is M2 minus M1, and you get the volume of the container or the mold, and you divide M by V. You get the bulk density. Now a small mass of the soil is taken then and is kept for actual water content determination, which means this will actually help you to determine the dry density. From M and the volume, what you get is bulk density, and once you know the water content, you will get the dry density, right? Calculate the dry density. And then the soil is removed from the mold and remolded and mixed with the next increment of water, and the test is repeated. So initially you take, let's say, around 4%, you fill it to the mold in 3 layers, 25 blows, calculate the mass which has actually gone into the mold, divide it by the volume, you get the density, find the water content. From the water content and the bulk density, you get the dry density. So that was one test, just one test. You repeat the process with an additional water content, let's say about 6%. Likewise, you add 8% in the next increment, 10% in the next increment. Likewise. So for each test, what you get is the dry density and the water content. Now, like I said, standard Proctor test is one test, the popular one in the Proctor test, but you have what is called as a modified Proctor test as well. The mold is the same, but the hammer is 4.8 kilogram, a heavier one, and the free drop is not 31 centimeter, instead it's 45 centimeter. And the soil is filled in 5 layers, each layer given 25 blows, right? And if the percentage of soil retained on 4.75 millimeter sieve is greater than 20%, you get a larger mold. Not the mold of a standard Proctor test, but a larger mold. Here comes the key point. On using a larger mold, instead of 25 blows, you use 56 blows for each layer. If the percentage soil is written on 4.75 mm sieve is less than 20%, you go with the standard mold and you stick on to the 25 blows, right? So the choice of the blows depends on the percentage of particles retained on 4.7